Hello, everyone. Good afternoon. Welcome, welcome. Hope you're doing well. So I think I answered a couple of questions there in the chat. If you, Zuo, if you still have questions about that, hang out after class and I can address that further. Okay. I see there's another question here before we get started. Taylor.
Yeah, it's on the second integrated rate law.
Yep.
Can you write the concentrations as negative exponents, or is it just easier to keep them fractional?
Sure. You can write a of t to the -1.
Yes,
Is that what you mean? Yeah, that means the same exact thing. So that's not a problem.
it doesn't change the concentration or
Doesn't change
anything.
it, but it's just
Okay.
it's a little easier to work with like this.
Okay.
It's just a little easier to solve for, in my opinion. But if you're comfortable with the negative exponent, that's fine too.
Okay. I agree. It's easier fractional. I was just
Yeah.
curious if there was a specific
Yep.
reason.
Well, I'll go
Okay.
over all this here in just a second.
Okay. Thank you.
Yeah, you're welcome. Let's see. Are there any other questions about anything before we start? I know I've already made this announcement. You know that we have an exam on the horizon, right? On February 11th. So keep that in mind. Thursday, February 11th. That's coming up. We are finishing up the kinetics chapter right now, right? So that's chapter 15. And we should finish that up in the next couple of days. And then we'll do a little review session for the exam. And then we'll have the exam. The pretest will be showing up on Mastering Chemistry. And that pretest is due the day of the exam, right? So that's a way that also counts for credit, of course. And so the exam really has two parts. It's the pretest, which you take online on your own time with any resources you want. And then there's the actual exam, which you take at a specified date without any resources except for the ones I specified. Okay. All right. Are there any other questions before we get going today? Megan.
I know you said that you would open the exam at 11 next Thursday. What time does it close?
Midnight.
Midnight. Okay, thank you.
And what did I say? I think it's 70 minutes. 70 minutes is the time. Yep. Good. Allison Walker.
Hi, when does the pretest open?
The pretest opens a week from Thursday. So it'll open, what's today, Wednesday? It'll open tomorrow.
Okay, great. Thank you.
Yeah. Good. Any other questions before we get going? Okay, well, I hope everything's going smoothly for you. Of course, you know, if things aren't going smoothly, send me an email, right? We can meet on Zoom and I can help you. And if you have any other questions, of course, that you want to ask, I'm always going to be here after class for as long as I need to be, and answering questions. And then obviously on Tuesdays and Thursdays, if you have additional questions, you can set up an appointment with me on those days and I'd be happy to help you, okay? All right, so we are working on kinetics. So remember, kinetics is the rate of chemical reactions. We're looking at the rates of chemical reactions. We've learned how to define the rate, right? So if you have a written reaction, you can write the definition of the rate. We've learned how reactant concentration affects the rate, right? And that depends on the type of reaction, or more specifically on the order of the reaction, right? Zero order, first order, or second order all have different relationships between rate and concentration, right? But generally speaking, except for zero order reactions where the increasing the concentration has no effect on the rate, for first and second order reactions, increasing the concentration increases the rate, okay? And then last time we barely scratched the surface of the integrated rate law, right? The integrated rate law gives us very practical information. It tells us how the concentration changes with time, okay? Concentration versus time. So for example, if we have a certain amount of reactant and we start a reaction, how much do we have in half an hour, right? Those kinds of questions. Those kinds of questions, you hear a question like that, a reaction starts with 1 molar, blah, blah, blah. How much is left after 10 minutes? Boom, you should think, integrated rate law. Concentration changing with time, okay? Now, the thing about the integrated rate law is that just like the rate law itself, right? Which is different for different orders. So the integrated rate law is different for different orders, okay? And last time we did a little calculus, which you don't have to know. And we came up with the first order integrated rate law, which is shown right here. The log of A of t is equal to minus kt plus the log of A0. What do all these things mean? A of t is concentration at time t, right? K is the rate constant, right? We've seen that before. The rate constant here is the same one that's in the rate law, right? Rate equals K a to the something. It's the same constant, right? T here is time, right? And A0 is initial concentration. All right? That's the initial concentration. So concentration at time t, rate constant, time, initial concentration. All right? So notice what you get with this reaction. If you know the initial concentration and you know the rate constant, you can find the concentration at some later time. All right? And we'll do an example of that in just a minute. What I want you to notice about this, though, is that it parallels the form for an equation for a straight line. Okay? So if you think of this equation, log of A of t minus kt plus log of A0, if we make y log of A of t, if we make m, if we make this the slope, tx, right? And then b is log of A of 0. In other words, if I make a plot where I plot log of 0, right? If I plot y versus x, which is time, right? Because these correspond, then what's my slope? Negative k, right? What's my y-intercept? Natural log of A0, right? So this is a good way to measure the rate constants for a reaction, right? If it's first order. It's also a good way to determine if a reaction is first order, right? So remember before we looked at one method of determining the order of the reaction. That was the method of initial rates, right? We had some initial concentration and we looked at the initial rate. We doubled the initial concentration and then we saw what the change was in the rate, right? And we figured out the order of the reaction that way. Here's now a new way to figure out the order of a reaction. You just take data of the concentration versus time, and then you make a plot, not of concentration versus time, but of the log of the concentration versus time. If that's a straight line, then we know it's first order. Okay? Now, just like we could take the rate law and integrate it and get the first order integrated rate law, we can take the second order rate law, integrate it, and get the second order integrated rate law. So this tells us exactly the same kind of information, right? Except this is for a second order reaction. It gives us the concentration of A at some time, given the initial concentration and the rate constant. All right. Now, notice the parallel for this equation and the equation for a straight line, right? Y is equal to mx plus b. What would you plot for a second order reaction in order to get a straight line? Can anybody see that?
Is it the inverse or the reciprocal?
Yeah, the inverse of the concentration versus
Positive k time, or
well,
your
what's
sorry.
x? Y and x, right? Y is going to be 1 over A of t. And what is x going to be?
Oh, time.
Just time, right? So for a second order one, I'm going to plot 1 over the concentration versus time. That's going to give me a straight line. What's the slope going to be equal to in that case? See the correspondence here? What's the slope?
Positive k.
Positive.
Positive k. Okay? Positive k. And the intercept, instead of being the log of A0, is what?
The inverse of A0.
The inverse of A0, right? Does that make sense? Okay, same thing for a zero order reaction. again, we have the rate law, right? The rate law in each of these cases, remember, the rate law for this is rate is equal to K A to the 1. The rate law for this is rate is equal to K A to the 2. And the rate law for this is rate is equal to K A to the 0, right? Remember, those were the rate laws for those different orders. And then, again, if you take this and you do the whole integration thing, you come up with this equation, okay? This is the integrated rate law for a zero order reaction. And what would you plot in this case to get a straight line?
So A of t is your y,
Yep,
and then negative k would be your slope.
yep,
Time is still your x variable there,
yep,
and then
yep.
just A of 0.
Exactly right, is B. So there it is. If I plot A as a function of time, I'm going to get a straight line, right? My slope is going to give us minus the rate constant, right? So here's a new way to figure out the order of the reaction, is just by measuring concentration versus time and trying plotting that in different ways, right? So let's see how that works. This table, by the way, in your book, table 15.2, is really a good table that summarizes all these things we've been looking at, right? Here's the order of the reaction, the rate law, the units of the rate constant K, because the units are different for the different orders, the integrated rate laws, 0, 1, and 2, what you plot to get a straight line for the different orders, right? And then half-life expressions, which we'll get to in a minute, okay? But here's what I mean about plotting data to figure out what the order of the reaction is. So let's say we have this reaction. So we do an experiment and we start a timer. And as a function of every 50 seconds or so, we take a measure of the concentration. All right, so initially we start out with 0.1 molar of this reactant, and then it drops to 0.0905 and so on. Okay, so I have this data. Now, the first thing I want to ask myself is, what's the order of this reaction? Well, if I just plot concentration versus time, I get a plot that looks like this. Okay, the concentration starts there, and that's just this data, right? I'm just plotting this data, and as time goes on, the concentration goes down and down and down and down and down. Okay. What can you conclude about the order of this reaction from this plot?
It's not 0.
Right. It's not zero order because look, if it was zero order and I plot A versus time, what would I get?
A linear line.
A straight line, right?
Straight
I would get
line.
a straight line. Did I get a straight line here when I plotted concentration of A versus time? No. So I know it's not zero order. Okay, well, let's try plotting something else. What if I plot the natural log of the concentration versus time? Ding, 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 ding. Bingo, right? Straight line. If I take that data and I just take the log of all these numbers, right? So in a spreadsheet, this is super easy. You just form a new column and you take the log of all those numbers, right? And then you make a plot of the log versus time. Boom, there it is, straight line. So by plotting this, I have identified the order of this reaction. What order is this reaction?
Is it second order?
No, let's go back to here.
First order.
Oh, it's first order
There.
because it's negative k.
The natural log of A versus time. If I plot that and I get a straight line, then I know it's first order. Okay, then I know it's first order, yeah? So I know that this reaction is first order. And if I fit this data to a line, what is this value right here, which is the slope, right? Y equals mx plus b. What does this value give me? Or what's that value equal to?
Equal to k.
Negative k, right? This is equal to negative k. Okay. Does that make sense so far to everyone?
Sorry,
Questions?
that value is equal to negative k. So like k in this scenario would be positive 2.01.
K's
Okay.
are always positive. Remember, rate is equal to k. K's are always positive. Okay. In this case, the slope is negative, but K is equal to minus the slope. So K would be equal to plus 2.01 times 10 to the minus 3. Yeah? All right, here's another reaction. 2NO2 goes to 2NO plus O2. Here I have partial pressure, which is proportional to concentration. So that's fine. I can plot partial pressure. I can measure partial pressure. So again, this same reaction. I start a timer every 30, this is hours. Every 30 hours, I take a measurement of the partial pressure, which is the concentration of the NO2. Okay, or proportional to the concentration of the NO2. So here's my data. So the first thing I do is I plot pressure versus time. Here's what it looks like. That's the same as plotting concentration versus time. Okay. So what can I conclude from this? It's the red line.
Again, it's not a zero order.
Again, it's not zero order, right? It's not zero order because if it was zero order, it would be a straight line like this black line. Okay, so it's not zero order. So I plot the log of the pressure or the log of the concentration versus time. The red line again. What can I conclude from this plot?
Not first order.
Not first order, right? Again, if I plot the log of the concentration versus time, a first order reaction would give me a straight line. This is not giving me a straight line, so therefore it's not first order. Okay, so I try the inverse of the concentration versus time, 1 over the concentration versus time, and ding, 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 right? There it is, my straight line, right? So what does that tell me about the reaction?
Second order.
Second order.
Second order, right? Second order. And for second order reaction, this slope right here, which is 0.0002, is equal to what?
Your K value.
Equal to K, right? Notice that for a second order reaction, slope is equal to K, right? Okay, very good. I know there's a couple questions here. I'm gonna go ahead and answer those. Minerva.
Hi, so I guess I'm a little confused on zero order and first order. So to differentiate the two, first order, you would have a positive K, like when you're given the information.
K's are always positive. The question is, when you make the plot, how do you get K from your plot? Okay, so in the case of a zero order and a first order, you get your K, the slope is equal to minus K. So K is equal to minus the slope.
Yeah.
But K's are always positive. All right, so the negative sign comes in because the slope in both of these cases are negative. So to get your K, you got to take negative the slope, which makes it positive. Does that make sense? But in both cases, for both a zero order and a first order, the slope is equal to minus K. But you're plotting different things, right? For a zero order, you're plotting A versus time. For a first order, you're plotting the natural log of A versus time.
Right. Okay. Okay. Now that makes sense.
That's the main difference. Yeah.
Yeah. Thank you.
Okay. Good. Other questions? All right. So now let's do an example of how we would use this equation to find the concentration of a reaction at some time. Okay. Which is what we said here, that this gives us concentration versus time. Okay. So I have this reaction. We're given that the reaction is first order, right? It has a rate constant K equal to 6.93 times 10 to the minus 3 per second. All right, we're given that the initial concentration, N2O5 at time 0, is equal to 0.100 molar, right? And we're asked to find concentration we're asked to find the concentration of N2O5 at T equals 1.50 times 10 to the 2 seconds. All right. So when you come across this kind of problem, you have to recognize it as an integrated rate law problem. All right. You got to say to yourself, I'm given the initial concentration. I want to find this concentration at some time later. Ding, 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 ding. That's integrated rate law. So to find this, I'm going to use one of these three equations, right? Which one I'm going to use depends on what the order of the reaction is, right? So what do they tell us here?
First order.
First order, right? So I'm going to use this equation right here. So I'm going to write log of N2O5 at time t is equal to minus KT plus the natural log of N2O5 at time 0.
One question, does minutes or seconds matter? Or should we always do in seconds for K?
So it depends on, you can do it depending on the reaction and how fast it is. Some reactions happen very slowly, in which case they'll report it in seconds. Some happen more slowly, in which case they might report it in minutes. Some even more slowly, which in hours, right? It doesn't really matter. The important thing is just to be consistent, right? So in other words, if you're given the rate constant in seconds, then what should you be using for time here? Seconds, right? If you're given the rate constant in hours, right, then you should be using hours there. Okay. So as long as you're consistent, it doesn't matter. You just have to use the same unit here and here.
Okay. Thank you.
Very good. Okay. So I'm trying to find this, right? I'm trying to find that. So I'm going to plug everything else into this equation. Minus K, 6.93 times 10 to the minus 3 per second times time, 1.50 times 10 to the 2 seconds. Ooh, what did I forget?
Negative sign.
My minus sign, right? So I need that minus sign. Plus the natural log of initial N2O5, which is 0.100 molar, right? Notice that my seconds cancel. That tells me that I'm using consistent units, right? And this comes out to be equal to negative 3.343. All right, but now notice that what I have so far is not the concentration. I have the log of the concentration at time t, right? How do I undo the log?
Raise it to the power of E.
Right, I raise it to the power of E, right? So I write E to the ln of N2O5 at time t is equal to E to the minus 3.343. All right. So your calculator might have a button like this that says E to something. The other button it may have, if it doesn't have the E, it may have a button that says inverse log. Right. That's the other possibility, inverse ln. Either way, either of those two do the same thing, right? It undoes the log. Okay. So E to the ln of N2O5, remember that E to the ln of X is just equal to X. Okay, that's the general relationship. They undo each other, right? So E to the ln of N2O5 is just equal to what? N2O5, right? And then you plug that number in your calculator and you find 0.0353, and that's always going to be in moles per liter. Does that make sense? Ryland.
So I understand the math. I just am curious, where does that moles per liter pop out from? Because it seems to me like all the units sort of cancel out throughout this.
Yeah.
throughout this.
So
It's the molarity.
I'm simplifying this a little bit. Yeah, it's molarity. That's correct, Diana. I'm simplifying this a little bit. For our purposes, all you need to know is that the concentration, when I write this, I always mean concentration in molarity. Okay, so that's the practical answer. The theoretical answer is that all of these concentrations, like I write here, in a more rigorous approach, are replaced with activities. And activities are concentration divided by some reference concentration. So usually that reference concentration is 1 molar. So that's where, that's kind of, I know it sounds a little hand wavy, and it is, but that's just the way it is at this level. Okay. It's a good question though, because I know I've always told you to be religious about units, and here I'm just popping out units out of nowhere. That's not very satisfying, I know, but for this and next chapter, when we get to equilibrium constants, we're going to see that the units aren't going to be as satisfying as we'd like. All right. But it's the way it is. Yeah, Abe. Abe?
Yeah, so when it comes to 0, first and second order, all those are like calculated experimentally, right?
Correct. You figure out the order of a reaction from doing an experiment. Yep, absolutely.
Okay, gotcha. And then so how exactly? Sorry.
No, nice background.
Yeah, no, I was just gonna say
that couple is definitely checking you out.
yeah. No, I was gonna. Sorry, give me 1 second.
Did you have another question?
Yeah, no, I was like, how like what? How exactly do they calculate it experimentally? Like what exactly?
How do they calculate what?
The order, like
Oh,
the like.
I showed you 2 ways, right? The method of initial rates, right? Where you look at the initial rate at different initial concentrations, right? What we did last time.
Yeah.
That's one way to do it. The other way to do it is to measure the concentration of a reactant as a function of time and make these different plots and see what the order is.
Oh, okay.
Right? So those are the experiments that determine the order.
Okay, great. Thank you.
That allow you to determine the order. Okay. Now, notice I use the first order integrated rate law here, right? What if the reaction had been second order? The problem would be identical in every way except for what?
The equation.
The equation. I'd use the second order equation for a second order, right? And of course, if it was 0 order, I'd use the 0 order equation. Okay. So it's just a different equation depending on the order of the reaction. All right. Oh, I see a couple more questions. Diana.
When we're doing these equations, will it always be stated what order we're solving for, or like what order?
Well, for this kind of problem, you will have to know the order somehow in order to know what equation to use. So if the problem doesn't tell you the order, it would have to give you some clue that allows you to figure out the order.
Okay.
For example, here it says it's first order, but it could have said a reaction in which the natural log of the concentration versus time produced a straight line has a rate constant, blah, 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 blah.
Oh, okay.
And then you would know from that, oh, since the natural log of the concentration versus time produced a straight line, I know that that's first order.
Okay.
Does that make sense?
Yeah.
Gabby.
Yes. Do we have to memorize all these equations, or you will give it to us?
You have to memorize all these or write them on your cheat sheet.
Okay.
Okay. So either memorize them or write them down. These will not be given on the exam. I generally do not give equations on any exams. I give constants, periodic table, but no equations.
Okay.
Because that's something you need to know. Emily.
So it was back to the units on that example that we just did.
One more time?
It was about the units on that example that we just did.
Yeah.
So wouldn't the molarity, when we wrote down the equation, the molarity right there at, when you wrote natural log of 1, wouldn't that be molarity?
This is also molarity, yes.
So
But the
is that
funny
where
thing
we get the moles per liter from? Because that never cancels out.
No, not really. Because when you take the log of a number, then you got like the log of the units too, right? So
Oh, I see.
it's-
Okay.
The problem is that this really is not molarity, it's activity, which is molarity divided, which is concentration divided by a reference concentration. So in other words, these are all, I wrote 0.1 here, right? But really it's 0.1 molar divided by 1 molar. So the units here cancel.
Okay.
I'm not doing it in that detail. We're just going to fudge the units a little bit, which I know is not very satisfying, but it's just the way we got to do it. Minerva.
So my question was in regard to Diana. So you know how she was asking, like, we'll have to have some type of clue to know which order it is.
Yeah.
How would we distinguish between like 0 order and 2nd order? Because for 1st order, you said that it would say like, oh, there's a straight line. So what type of clues could we look out for like
Sure.
0?
So for a 0 order, right, you would plot what to get a straight line?
Decreasing linear line.
You would plot concentration versus time. So in other words, a clue up for a 0 order reaction would be, hey, if you plot the concentration of the reactant versus time, you get a straight line. Immediately you think, that's a 0 order reaction.
Okay.
For a 2nd order reaction, you would plot 1 over the concentration versus time. So if you hear a reaction in which you plot the 1 over the concentration versus time gives a straight line, you go, that's 2nd order. 1st order, log of the concentration versus time. See, these are the 3 different things you plot that will reveal what the order is.
Okay, so we could expect to see like something that has a sentence that says that, or like given a graph that has that information on there.
Yeah.
Okay,
Yep.
Thank you.
You can't do this kind of problem without somehow knowing the order of the reaction. Okay? Because you need to know which equation to use.
Yeah, okay, thank you.
All right, awesome.
Could you also give us just like the data from the experiment like we used in last class?
Sure.
And from that we could, turn the order and do it there.
Yep, absolutely. Okay, so associated with sort of this integrated rate law is something called the half-life. So I want to, I'll derive the expression. So let me just first define half-life actually. T1 half equals half-life. And it's the time required for the initial concentration of a reactant. Time required for the initial concentration of a reactant to fall to 1/2 of its initial concentration. Okay, the time required for the initial concentration of a reactant to fall to 1/2 of its initial concentration. So let's say we have a reaction, and let's say these blue particles represent the reactants, only the reactants, and the products are invisible in this little picture. Okay, in these pictures the products are invisible, and all you're seeing is the reactants. All right, the half-life is the time it takes for the concentration to fall to 1/2 of its initial concentration as the reaction proceeds. Right. So see here, in this case, the half-life is 100 seconds, right? So in 100 seconds, it goes from this many particles to half that many. That's one half-life. Notice now this becomes the initial concentration. In another half-life, this falls from this many particles to half that many again, right? And here, same thing. After another half-life, 100 seconds, in this case, it's 100 seconds, it'll fall from that concentration to half that again. And it'll just keep going. All right? So, in other words, we can express that mathematically like this. When T is equal to T1 half, then A of T is equal to 1/2 A of 0, right? When time equals a half-life, the concentration at that time is equal to 1/2 the initial concentration. Can you hear me okay? Am I having problems with audio? So we can use this definition to come up with an expression for half-life. All right. So let's start with first order. So we know for a first order reaction that the log of A at time t, right? Again, from our this master.
I think it's my connection.
It's your connection. Okay. From this master table, we can get these expressions, right? So this is a good master table to have at your fingertips. Log of A of t is equal to minus kt plus the natural log of A0, right? For a first order reaction. And then I'm going to use this definition and I'm going to say, okay, when t is equal to T1 half, A of t is equal to 1/2 A0. So what I'm going to do is I'm going to substitute in. I'm going to substitute in t equals T1 half here, right? And I'm going to substitute 1/2 A0 into there, right? So I'm going to get, actually I should do one thing before I substitute in. Hold on. I want to rearrange this equation a little bit before I substitute in. Remember, I'm going to rearrange it like this. Log of A of t minus log of A0 is equal to minus kt. All right. And remember, log A minus log B is equal to what?
Log A over log B.
Yeah.
Log A over B, right? So I can say log of A of t over A0 is equal to minus kt. All right, now I want to substitute in. So I'm going to substitute T1 half right into there. And I'm going to substitute 1/2 A0 right into, oops. Oh, let's see. Right into there. Right? A of t is equal to 1/2 A0. So what do I get? I get that the natural log of 1/2 A0 divided by A0, right? The natural log of that whole thing is equal to minus kt 1/2. Oops, I just for some reason forgot to put the rest of that in there. Yeah? Does that make sense? So then notice my A0s cancel and I get ln of 1/2 is equal to minus kt 1/2. So I get T1/2 is equal to log of 1/2 divided by minus k. Log of 1/2 is minus 0.693 divided by minus k.
Can you move the paper up, down?
Sorry.
No worries.
Log of 1/2 is equal to minus kt 1/2, right? So I'm solving for T1/2. So T1/2 is equal to log of 1/2 divided by minus k. Log of 1/2 is minus 0.693 divided by minus k. So I end up with this expression. Oh, I can't write. T1/2 is equal to 0.693 over K.
Can you scoot it down a bit to make sure I didn't miss anything from above?
All right, so this is the important conclusion right here. The relationship between the half-life and the rate constant, okay? I can do the same kind of derivation for the other half-lives. I won't do all those derivations. I'll just give you the results. So this is for a first order, right? For second order.
Sorry, Professor, my connection was lost and I missed for the first order, the derivation you did. Or the, just a little bit more up. Could I see? So, and now I'll just take a screenshot so you can.
Yeah,
keep
take a
going.
screenshot.
Thank you.
Okay.
Thank you.
Yeah. So for second order, the expression is T1/2 is equal to 1 over KA0. And for zero order, the expression is T1/2 is equal to A0 over 2K. All right. So notice that just like the rate law is different for the different orders, and just like the integrated rate law is different for the different orders, so the expression for half-life is different for different orders. All right, and if I go back to this master table here, I have all the information nicely organized in one table. All of this is information which you'll have to know, right? Zero order, here's the rate law, integrated rate law, what you have to plot to get a straight line, and then the half-life expression, right? So for zero order expression, it's that one, right? For first order, rate law, integrated rate law, two different forms of it. What you plot for a straight line, half-life expression. Second order, rate law, integrated rate law, what you plot for a straight line, half-life expression. Notice one thing that's unique about the first order half-life expression. What is unique about the first order half-life expression compared to the other two?
It has numbers
It's a
like
ratio. Oh,
Go ahead. I didn't hear you.
has a number associated with it.
Okay, it has a number associated with it. It has 0.693. Well, this has number 2 associated with it.
It doesn't have the concentration.
The important thing is it doesn't have the initial concentration. Okay, notice there's no dependence on the initial concentration, right? That means that that's why this concept of half-life is super useful for a first order reaction. All right, it's useful for zero order and second order too, but it's most useful for first order because it doesn't depend on initial concentration. Diana.
I had a question on how you did first order. Do you mind scooting up the paper a little bit? I don't know if I copied it right. So you have ln of it's the initial concentration of T over the initial, right? And then they just cancel each other out.
They cancel each other out when I substitute A of T is equal to 1/2 A of 0, right, into here, right? Then I get 1/2 A of 0 over A of 0, and those cancel out. So that's how come the initial concentration cancels out.
So why is it that we have the half in the top of the ln? When you cancel them out?
Because the half doesn't cancel, right? Because remember what I'm doing. I'm saying A of t is equal to 1/2 A0. So A of t, this whole thing is 1/2 A0. So the half doesn't go away. So it ends up being the log of a half, which is where you get that 0.693.
Oh, okay. I missed that part.
Taylor.
Thank you.
If you were gonna do the half-life again, would it just be the same process? Does that make sense?
Half-life again.
Like the second half-life, because there's
So it would just be 2 times this,
okay.
right?
So
So,
it's just
2 half-lives would just be, so if the half-life is 100 seconds, let's go back to this plot. If the half-life is 100 seconds, right, then for a first order reaction, only for a first order reaction, the second half-life would also be 100 seconds. Okay, good point. That's not true for 0 and second order reactions, again, which is why this concept is most useful. For a second or 0 order reaction, the half-life changes after each half-life, right? Because you'd have to put in the new initial concentration to get the new half-life.
okay. So to simplify that, so for first order, it's kind of a constant,
Correct.
and
The
then
half-life-
for sorry.
Yeah, go ahead.
And then for 0 and second, you have to do it for each specific.
Correct. You'd have to plug back
Okay.
in to, after every half-life, you'd have to plug back into these equations to get the next half-life. Good. All
Thank
right,
you.
let's do a quick example using half-life. First order reaction, A goes to product, has a half-life of 10 hours. What percentage of A is left after 30 hours? And look at that, can you believe it? I'm going to actually launch a poll and it's going to be numbered correctly.
You don't have the answers though.
Oh! Ah, such a dork. Okay, hold on. Give me a second. Oh, okay. You know what? Let's actually, I know why. I see why I don't have the answers, because I didn't mean this to be I meant this just to be an example. So let's just do the example and then I'll ask you a question. That's what happened. Okay. So a first order reaction, A goes to products, has a half-life of 10 hours. So I got A goes to products. I'm going to shut down that thing. A goes to products. I know that half-life is 10 hours, right? And I know that this is first order, so I know that it's always going to be 10 hours no matter what, okay? And I'm asking the question, find percent left after 30 hours, okay? So one way I could do this, of course, is to use my first order rate law, right? And put 100% in here, right? And put t equals to 30 hours in here, and find A of t, which is, you could just say, even though this is in molar, it'll be proportional to 100%, so that's fine. So you'll get some number proportional to 100, right? And that'll give it to you. So that's one way to do it. But the other way to do it with the concept of half-life is just to make yourself a little table, right? And say A versus time, right? So at time 0, we'll say 100% of A is present. And then if the half-life is 10 hours, right? How much of A do I have after 10 hours?
50%.
50%, right? How much do I have after 20 hours?
25%.
25%. How much do I have left after 30 hours?
12.5.
12.5.
Does that make sense? Okay. All right, here's the question I have for you. This is a little bit of a tricky question. All right, so I'm gonna let you go ahead and try it first here, and then I'm gonna give you a clue in just a few seconds. Okay, so just read it over. And the reason it's tricky is because of this x goes to 2y, right? You have to take into account not just the half-life, but you have to take into account the stoichiometry. Okay, let me give you a little hint here in case you're struggling. So you could set up a table just like we did, right? So you can have a table where you have x, y, and time, right? So it says, if you start with 1 mole of x, so you start 1 mole of x, 0, 0 at time 0, right? And you got to remember that x goes to 2y, so keep that in mind. All right, I start with 1 mole of this, 0, 0. After 17 minutes, that's 1 half-life. How many moles of x do I have?
0.5.
0.5, right? That's a definition of half-life. Now I'll let you take it from there. Okay, let's see a few of you. A lot of you that have voted have gotten it correct, but some of you haven't voted yet. What's going on? Please vote. Please vote. It's important for your learning to vote, to participate. Here's another little interesting statistic from education research. A lot of times, if you're gonna learn something, it's actually better for your learning to predict. Let's say you're going to learn. Let's just say you were going to learn whether vaporization is exothermic or endothermic. Okay, let's suppose that. So let's say before you learn it, you're asked to predict. What do you think? Is it going to be endothermic or exothermic? Answering that question, even if you answer it wrong, helps you to learn it better. Isn't that weird? And here's kind of why, right? So I'm not a big sports on TV fan, but I watch the Super Bowl every year. Okay, so it's the one football game that I watch because, well, I like the halftime show and stuff like that, right? Anyway, so I always wonder why, man, these people seem so into it. Like I'll have little Super Bowl party with some friends or go with some friends to watch it. And they're so into it. And I wonder, well, why are they so into it? Well, they're so into it because they have taken a vested interest, right? They are rooting for a team because they've invested themselves in that team over the entire season or whatever, right? So a few years ago, I decided I'm going to start rooting for a team. And I don't care what team it is. I'm just going to pick one, right? And when I started rooting for a team, all of a sudden the whole game became more interesting to me, right? Why? Because I had a vested interest. So if you're going to learn something and you haven't learned it yet, take a guess at what you might think the answer might be. Let's say you're trying to answer a question. Take a guess at what it might be. And believe it or not, it turns out that that guessing process helps you to learn it better because you have a vested interest and you learn it better as a result. Isn't that weird? It actually, there's data that backs that up too in education research. So, okay. My point is that even if you get some of these poll questions wrong, they're gonna help you learn. So participation is key, right? Take a side, right? Don't be like me and waste all those years watching the Super Bowl without taking a side. Wasn't very interesting to me any of those years. I liked the commercials and the halftime show. Now I actually like the Super Bowl because I actually picked a side. All right, end polling. So we did okay. A lot of you picked A, which was the right answer. But some of you did pick B and a few picked C. But let's just finish filling out this table so you can see what happens here. So the tricky thing about this is that this is a first order reaction. So we know that it goes down from every half-life, right? It goes down by 50%, right? That's the definition of half-life. So you start out with 1 mole. In 1 half-life, you have half a mole. In 2 half-lives, you have 0.25 moles. In 3 half-lives, you have what? 0.125 moles, and so on, right? Now, this half-life problem becomes a stoichiometry problem, right? If half a mole of X reacts, how many moles of Y are formed?
2.
No.
1.
1. If 1 mole of X reacts, I get 2 moles of Y. But if half a mole reacts, I get 1 mole of Y, right? When 0.25 moles, when 0.25 moles of X are left and 0.75 moles have reacted, right? How much Y do I have?
$1.5.
1.5.
Correct. 1.5. Right? So after, what's that? 17, 34, 44, 47, 47 minutes. Is that right? 30. No, man,
51.
I can't think. 50, 34, 54 minus 3, 51, right? 51 minutes? 3 half-lives? Yeah. Then how many moles of Y do I have? Well, how many have reacted? Oh, I can't do the math. I'm too I can't do this math in my head.
It's 0.875.
Thank you. 0.875. And if I multiply that by 2, I get 1.75. So this is 1.75 here, right? So notice the concept of half-life and then the stoichiometry, right? So the answer was A, right? Because it's asking how long until I get 1 mole of A, right? So it's 17 minutes. Whew, Megan.
Could you almost think about it like the reciprocal of what's happening on the reactant sides with the product?
Yes.
Okay.
It's not really the reciprocal. It's basically the whatever reacts here, the amount that it goes down here goes up here, but you have to take into account the stoichiometry.
Okay.
As
Do you
this goes
mind
down,
also-
that goes up.
Okay. And could you explain why when we start with 1 mole of X, 0 moles of Y at the beginning? If we're looking at the equation.
Oh, I'm just saying that's so you have a reaction mixture and you don't have any products initially. You just start with the reactant X. And then you just let it react. Emily.
I just lost you a little bit with the numbers. I'm confused why we have 51 minutes from, you know, you're like 0 to 17
Oh.
and then 17 to 34 is double. So how do we get that 51?
Oh, okay, yeah, good. So this is 1 half-life. This is 2 half-lives. This is 3 half-lives. Right? 17 minutes, 34 minutes. Let me go back to this plot because I think this will help you to see it a little better. Right? So here's T0, you have 100%. 1 half-life is 100 seconds. It goes to 50%. 2 half-lives is 200 seconds. It goes to 25%. 3 half-lives is 300 seconds. It goes to 12.5%. Does that make sense?
Yes, that helps visualize for sure.
Awesome.
Thank you.
And so when I was doing this, I got it correct for the first one. But then when I went to do the 0.25 moles, I was just doing 0.25 times 2. So I wasn't really getting 5, I was getting 0.5. Do we have to add something from the equation?
No, here's what happens, Sophia. You have to, this is the amount, what I'm plotting here is the amount of X that's left. But in order to get this number, you have to figure out how much of X reacted. Right?
Okay. Okay, so
in other words, you start out with 1 mole of this. You go down to half mole reacts, so I end up with 1 mole of that, twice that. When I get to here, how many moles of X have reacted? 0.75 moles. So if 0.75 moles of X react, how many moles of Y form? 1.5.
Okay,
Does that make
makes
sense?
it more clear. I was like, okay, so should I add that to what's left? Okay, that makes sense.
Yeah, that's what it is. Good question.
Thank you.
Tricky little problem. Let's see, are there other questions on this? Okay, here's another little tricky problem. I'm going to let you read through this, and then I'm going to go ahead and launch this poll, but don't answer necessarily right away because I'm going to put up that table in a minute so that you can look at all the different half-lives and those relationships. Okay, so just read the question thoroughly. I'll give you about a minute to read the question thoroughly, and then I'm going to pop back over to that table, or let's see. Oh, I wonder if I can. I think I can just put the table up over here, right? That would make it easier. Hold on.
Wait, I don't know if it's just me, but I can't see the question.
Yeah, sorry. I know. I'm not doing a very good job here. Shows you my computer incompetence. Just say, okay, boomer. Why won't that work? Can you see my screen?
Yeah.
What the heck?
Maybe 2 PowerPoint slides and just get rid of the camera feed.
Yeah, I was just hoping I could do it. Let me just try this one more time. Wow, my computer's just really slow for some reason. Oh, duh. Sorry. Oh, there we go. Okay. Did I launch the poll? Yeah. This is a really tough question, and you have to really understand the different orders and their properties in order to answer it.
Professor, there is something in the middle of the screen and it kind of covers a little bit of the,
There we go.
like a black.
Ah, there we go.
Does that work now?
All good.
Oops, sorry. Okay, I'm gonna just give you a 10 or 15 more seconds and I'll close this up. It looks like almost all of you are getting it, so this is awesome. All right, I'm gonna go ahead and end it right here. Nice, thank you all for voting. That's great. So most of you put A and most of you voted, and A is indeed the correct answer, right? So nice work. You can see that the reaction A to products has a rate that is observed to slow down as the reaction proceeds. So once you read that, you know that it can't be zero order, right? Because zero order reactions don't slow down as they proceed. They have a constant rate, right? So as A changes, the rate doesn't change for zero order reactions. As A goes down in these two, the rate does go down, right? So you already know that it slows down as the reaction proceeds. And then you have a half-life that is independent of the initial concentration of A. Oh, ding, 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 ding. That tells you right there the order of the reaction, right? What is it? First order, right? So which of these is true for a first order reaction? A. All right. So nice job. All right. Any questions? Can I show you guys something I'm kind of excited about? Do you mind? This is the next thing I'm building for my book, and they're called interactive. So, you know, my belief in like the more active you are, the better you're going to learn, right? The more you're participating. So one problem with reading is that if you're just reading passively and not answering questions or anything, right? You're passive and you don't learn very well. So I've been building these little interactives that force you, this will be in the ebook, will force you to constantly interact. So this is just one on unit conversions, right? So you start with this and it says, okay, it shows you how to do a unit conversion. A marathon is 26.2 miles. Convert this from miles to kilometers, right? And then it kind of explains what's going on. Unit conversion problems like this one are a central part of problem solving. Many chemical problems can be organized and carried out this way, right? So then you go to the next one. To solve a unit conversion problem, you must find the relationships that will allow you to convert from given to find, right? So now you have to think, right? Now you have to think, what relationship is required to solve this one-step problem? Well, you have miles and you're going to kilometers, right? So you got to think and you got to go, oh, okay, this will. Check answer. Yay, you're correct. Now, let's suppose you answered the wrong thing. Oh, wait, I gotta renew it. Why won't it renew? So if you answered the wrong thing, they'll say, no. You gotta focus on the units that are in the problem, right? So it gives you constructive feedback, right? Until you try again and then you can get it. And then you just move on and it's the same kind of thing. So then to solve this problem, you got to build the conversion factor, right? So then it asks you, okay, what's the correct form of the conversion factor, right? So you got to just constantly, so you're not just reading it passively, you're reading it actively, right? So every step of this, you're being active. Anyway, just for fun. Had a couple extra minutes. I think that was a lot for today. I don't know if I want to start on the next topic at the end of class because the next topic is a little bit involved. So I think I'll stop right there and I'll see if there are any more questions. I'll answer them. Otherwise, I'm going to dismiss you. And those of you that want to stay can stick around. Let's see, Taylor.
So I have 2 points. So this replaces the chapters, or like not the chapter, but the quizzes at the end. Sorry.
No, this would be an additional feature where you're saying, oh, okay, I want to learn about units conversions, but I don't really read about it. So you click on this and it would open up and then you would step through it, right? The hard thing about this is that you're it'll be interesting to see how it works, is you're constantly going to have to answer questions to get through this, right? But it'll mean that you'll learn it much better than just passively reading it.
Okay.
Right? At
so
least
like a
that's what
Quizlet?
What?
Sorry, like a Quizlet?
It's kind of like, it's a little bit like, so I try to do this a little bit with the videos, right? Where the video stops in the middle and asks you a question and forces you to interact. But instead of just one question here, there's going to be 5 or 6, right? So you're constantly having to interact in order to learn it.
Okay.
Does that make sense? And it won't be a video. It'll be like this. It'll just be you read, and then you answer the questions.
Okay. That seems cool. I'm excited for that. It looks cool.
I think I'm super excited. I'm gonna build 50 of them and
Nice.
see how it goes.
All right.
Ryland.
I just had a thought about half-life, which is if things are always decaying at their half-life, how do they ever reach 0, or do they just get so close to 0 that it's insignificant?
Oh, great question. You're right. So if it just keeps approaching 0 asymptotically. And you're absolutely right. It never gets all the way to 0. So at some point, there's gonna be 1 atom left or something.
Cool.
Yeah. Alex.
Hey, so I had a question about like the rates of change of like the reactions that we were doing last class. Like in the homework, it asks you to find the instantaneous rate of change of the reaction. And then like it says like at 50 seconds, but then when it calculates it, it uses 40 seconds, you know, in the, like it divides by 40 seconds, or like it divides by like 60 minus 20 when it's asking for 50. Because like if you're taking the instantaneous rate of change, aren't you taking like the limit and then getting the like the tangent, like making the secant line into the tangent line? So I don't know, I'm just kind of confused.
I'll show you. You won't have to do this on the test, but the instantaneous rate looks like this. It's right here. So let's say you were trying to find it here at 50 seconds, right? So you draw the tangent, which is this black line right here, and you'd find the slope of that tangent, right? So the slope is the change in HI, which is 0.56. So it's this, you know, what is it? 60 something minus, no, sorry. 1.5 something minus 1, 1.56 minus 1. So that's 0.56. It's the difference between here and here. And then the time would be what? 70 seconds minus 30 seconds, which is 40 seconds. And then delta HI, delta T would be this divided by that. Does that make sense?
Yeah, that makes sense, but I'm confused how you would like.
The only way you can do this, is graphically, like literally printing out the graph, getting out a ruler, drawing a line, and estimating these points.
Because there's a question on the problem set that's like this, and it asks you to find the instantaneous rate. I just didn't know how to make like the tangent line.
Right.
Yeah, because I was confused. But then like I was reading the book too, and then it asks you to like do it, or it's like showing the example, and it says at 50 seconds, and then it just divides by 40 seconds.
Right. This
like
is
I'm
that,
assuming
this is,
that
this is that example, right? Because see, it's at 50 seconds, but the time interval covered by this particular tangent line that I drew is 40 seconds because it's delta T, not T.
Yeah.
Does that make sense?
Yeah, I think so.
Do your best to answer that question. I do want you to kind of be exposed to this concept, but it is a little difficult, and I won't be asking you it on a test.
Okay. Cool. Thank you. Yeah.
So sometimes on the problem sets, you know, I'll push you a little harder. Like, you know, for example, you had some half order stuff. I won't put a half order thing on the exam. Okay. But I do like to push you a little harder on the problem sets to see, because some of you can totally handle it, especially those of you that have a lot of background in chemistry. All right, it's 3:20, folks. Thank you for your attention. It's great to see you all. I will see you on Monday, right? See you all on Monday. If you need any help between now and then, drop me an email. I'll meet with you. Otherwise, have a great day. And see you Monday.
Thank you, Professor